Alrighty. So, in order to discuss the end behavior of a polynomial, we want to make sure we have one kind of key term down, and that is the degree of a polynomial. Okay. Does anyone have a recollection, or does anyone remember what the degree? How do you find the degree of a polynomial? What makes it a degree? Yeah, Ben. Okay, the exponent. Okay, yeah. Joshua, you want to add anything else to that?
It's the highest exponent.
Okay, right. So yeah, exactly. It deals with the exponent, and it is the highest exponent. Exactly right. Okay, the greatest power in the polynomial. So yeah, we'll say the largest exponent, right, in the polynomial. Okay. And the end behavior is like what happens as we go really, really far to the right, right? Or what happens as we go really, really far to the left. Okay. For our quadratics, right, our end, kind of like what happens at the ends, either they both go up for forever, that means they both go to infinity, right, positive infinity. Or if the parabola is kind of like upside down, right, looks like a frowny face, right, that means then the end behavior, it would go to negative infinity, all right, as we go either far to the right or far to the left there on our curve. All right, so two components help us determine end behavior. So to determine end behavior, okay, consider, we'll put a little colon there. Consider two things, right? One, lead coefficients. I should just say the lead coefficient, really, and the degree of the polynomial. Okay. Yes?
How do you say lead coefficient? Do you mean the coefficient in front of the thing that's the highest exponent, or the one that's in the front?
Right, good question. So most of the time, like 90% of the time, that's simultaneous. So it's like that means the same thing, synonymous, I should say. Right, but it's not always. Good. So the lead coefficient is the coefficient of the highest degree term. Yeah, exactly right. Okay. All right. So right, 95% of the time, the polynomial will be in order from greatest degree on down. So you just take the highest powered term. It's normally in the front, but it's not always in the front. So be on the lookout. Right. Don't just assume. Don't just look at that first part, that first term, and assume, okay, well, there's my highest term. You need to look at all of them just to make sure. And then, of course, your lead coefficient will be the lead term with the highest degree. All right. So we're going to break this down here, trying to organize this some. So let's first start with even degree polynomials, because we've been working with those quadratics, and those are even degree, right? Their degree. What is the degree of a quadratic? 2, right? 2, because it's x squared. They all have an x squared with them. So even degree polynomials. Okay, and I'm going to, if lead coefficient, that is the number in front, when you have it in order, if the lead coefficient is greater than 0, okay, or if you like, you could say, or if it's positive, I'm going to put positive in parentheses. Right, because greater than 0 means positive. Okay, so that's like our typical quadratic that we see, where we have the shape like this. Right, positive a, because a is normally our lead coefficient in a quadratic. Positive a means both ends point upwards. I want you to be able to write it out though like this: as x approaches infinity, f of x approaches infinity, right? As we go far to the right, right, because x's go left, right, our function, right, or the y values, they go up, right? They keep going up. As you go farther to the right, the curve goes up towards infinity. And then as x approaches negative infinity, f of x approaches positive infinity as well, right? So as you go far to the left, right, negative x values more and more negative x values, they will go up towards positive infinity as well. Okay. 2. Let's now change it if the lead coefficient, so we'll still be even degree, if the lead coefficient is less than 0. Right? Well, that's going to reflect the graph, so now it's going to go downwards. Okay, and so now, as x approaches positive infinity, that means as we go farther and farther to the right, as we go further and further to the right there, what's going to happen? F of x will approach what? Negative infinity. And as x approaches negative infinity, that is, as we go further and further to the left, f of x will also approach negative infinity as well. Okay. End behavior and increasing and decreasing behavior, we describe them in kind of 2 different ways. Right? If you remember back when we were talking about where a function is increasing, where a function is decreasing, we always had to be sure that we were moving from left to right, right? Sometimes we get confused and say, oh, Mr. Witt, right, this part of the graph is increasing. Look, it's going up. And you might be tempted to describe that as increasing, but we're like, no, that's a decreasing part of the graph. Why? Because as you go from left to right, our curve is going downward, right? And you always had to concern yourself with going left to right, decreasing to increasing, right? But now with this, we're not always going left to right, right? So for example, as x approaches infinity, that is going left to right, and so it's going up towards positive infinity. That makes sense. But for this one, as x approaches negative infinity, we're now going right to left, and so we do describe this as an upward motion for this. We say it's going to positive infinity, right? So while we say this is decreasing, right, this part of the graph is decreasing, we also say as x approaches negative infinity, f of x approaches positive infinity. Right, so it gets a little confusing. It's a subtle, change there, but I think that's what throws students off. Okay, I guess I can put the word negative in there too. So just be careful, okay, don't get those increasing, decreasing, and then your, x approaches negative infinity, x approaches positive infinity stuff mixed up. So that covers even degree polynomials. Let's talk about odd degree. Okay. So in this case, we'll start again with lead coefficient being greater than 0. Okay, so if the lead coefficient is greater than 0, so you think about a cubic, right? Cubics look something like this. Okay, lead coefficient greater than 0. As x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches negative infinity. Okay. So as we go far to the right here, we're going to go up towards positive infinity. As we go to the left, we're going to go down towards the negative infinity. F of x will go down towards negative infinity. Okay. When you guys are writing these down, the only part that you really have to quote unquote think about, right, or the only part that that will change are these infinities here at the end, right? All of these start with as x approaches infinity, as x approaches negative infinity, f of x approaches, right? They all have that. It's what changes here at the end, whether it approaches positive or negative infinity for these polynomial functions, okay? That's all. All right, last scenario here. If the lead coefficient is less than 0, then as x approaches infinity, well, here it's going to look something like this. Right? So if the lead coefficient is less than 0 and it's an odd degree polynomial, as we go further to the right, f of x will go which way? Negative infinity. And as x approaches negative infinity, f of x will approach positive infinity, right? Because we're going up. We're going up. Yeah, we're going up. Oops, I'm off the screen. There we go. That's better. Okay. So again, it just flips. So if an even degree, either they both go up or they both go down, right? So even degree, the end behavior isn't the same for the left and the right. For odd degree, they will always be different from each other. Left and right end behaviors will be different. Okay? Questions on any of that? We'll get different end behaviors for other kinds of graphs, right? Some graphs will approach a single number as you go really, really far to the right or really, really far to the left, right? Some graphs can approach more than a single number as you go far to the right or far to the left. Well, you'll approach one number as you go to the right, one number as you approach to the left, that kind of thing. Some numbers won't approach any number, but they also won't be infinite either. We'll talk about those too later. Okay. So let's do an example now, finally, right? After all that preparation. Determine the end behavior of each function will be our directions here. I'll do 2, and then I'll have you do 2. Okay, so determine the end behavior of each function. Number 1. G of x equals 3x to the 4th minus 5x squared plus 4. Okay. So there's our polynomial. Okay. I'll go ahead and prepare us too, just with as x approaches infinity, f of x approaches blank. As x approaches negative infinity, f of x approaches blank. Okay. So for this problem right here, do we have what's our degree? 4. So that means the degree is even, right? And our lead coefficient is positive 3, so positive. Okay, so it's an even degree, positive lead coefficient, even degree, lead coefficient greater than 0. Our end behaviors are like this. So as x approaches infinity, f of x will approach infinity. And as x approaches negative infinity, f of x will approach infinity. That's right. Okay. Pretty straightforward stuff, right? Let's try another one. H of x equals x times x to the 4th minus 1. What is the degree of this polynomial? Square?
No, it's going to be 5th root.
Fifth degree. How do you get that? I see the highest power here is a 4. Why do you say 5? Yeah, okay. So this x, right, has to distribute to the x to the 4th minus 1 there, and so it becomes x to the 5th minus x. So the highest power here is going to actually be a 5. Even though you don't see it initially, it is 5. The lead coefficient is, well, so the degree is odd. The lead coefficient is positive. So let me write this out here. As x approaches infinity, f of x will approach, and as x approaches negative infinity, f of x will approach. Okay, so odd positive lead coefficient means it's going to look something like this, right? At the ends, at least. Well, I guess I'll say like this and then like this. So that means as we go far to the right, f of x will approach what? Infinity is right. And as x approaches negative infinity, f of x will approach negative infinity. There we go. More people chimed in there. Okay, questions on that? 1 or 2? You ready to try your own now? Yes? Okay. Here we go. Number 3. This is one for you to try. F of x equals negative x times x minus 2 times x plus 2. And then number 4, negative 13, oops. Let's say, I don't know, I'll say another h of x. H of x equals negative 13x squared minus 2x minus 5. Okay. So go ahead there. Try 3 and 4. If you want to, yes, that's fine. Yes, you can, yes. If you like. I can. Oh, what's that?
Wouldn't that just mean, could you just say shorthand is always approaching infinity then? Plus or minus infinity?
So, for example, number 1, a shorthand way to do this.
Well, that would only work for numbers, okay,
Right?
yeah.
That will work, right? That's number 1. Number 2, shorthand way. I guess we'll always put plus or minus there, right? Because it's all. And in this case, what I would suggest is. And I would understand that to mean, because you put the positive on top, negative on the bottom kind of thing. If they were flipped, then I would have you write it like this.
The second one isn't. That's different.
Say what now?
The second
They're different, that's what I'm saying.
Yeah.
So I'm saying, like, if you choose to write it like this as like a shorthand, I will understand it to mean as x approaches positive infinity, f of x approaches positive infinity, and as x approaches negative infinity, f of x will approach negative infinity. Like, if you keep the order the same, I'll understand them to match up. If you want them to be, so if you want it, well, let me just go ahead and say here. Let's get to this, right? So for number 3, then, okay. For number 3, what is the degree for number 3? Cubed, right? The degree is 3, so it's odd. And what's our lead coefficient? -1, right? We have a -1 plus a +1 plus a +1, so it's going to be -1 x to the third there. You know, dot, dot, dot. We don't need to worry about the other stuff there. And so that means then as x approaches positive infinity, f of x will approach negative infinity. And as x approaches negative infinity, f of x will approach positive infinity. So again, what I'm trying to demonstrate here, Joshua, the shorthand for number 3, you could do as x approaches plus or minus infinity, f of x approaches minus plus infinity, like that, and then I'd be. Okay, do you see what I'm getting at there, I guess? So, but that's your choice. I don't know if other teachers will be okay with this, but I mean, if you don't want to have to write it, but you can write it that way too. Was that the point you were trying to ask about? I don't know if I was even answering.
No, it's more for like the first one. First one and the fourth one.
Yeah. So you can definitely do it for this one, right? And then same thing for the fourth one for sure. Okay, right. And because number 4, then both the left and the right are going to approach negative infinity. because we have an even degree, but they're negatively coefficient there. Okay? Questions on 1, 2, 3, or 4? All right, enough end behavior. Now let's actually graph some polynomials. Well, bad news. We can't graph polynomials. Not as accurately as we would like to, at least. All right, because we don't have calculus. Without calculus, you really can't graph polynomial as accurately as you would like to. But we're going to try and get as close as we can being in pre-calculus. So, okay, so there is the polynomial that we're going to sketch. Right, when I say sketch, I mean this is really going to be a sketch. More so than our quadratics are sketches, more so than when we graph a line. Okay, this will actually be a sketch because this will not be as accurate as we can be. Or it'll be as accurate as we can be for right now, I guess. Okay, so what do I want us to include, when we are sketching the graph of polynomials, or what do I want us to find? So, right, x-intercepts, exactly right. Find the zeros. Which again, yeah, x-intercept. I'm not so hung up on getting the y-intercept. If you want to, that's your choice. But really the zeros, at least, okay, for the x-intercepts. And then I also like to evaluate. I want you to be able to evaluate the behavior between the zeros. Okay, I like to call that, it's not like an official mathematical term, I like to call that the middle behavior. Okay, what happens in between the zeros, in the middle of the zeros. And then finally, find the end behavior. Okay, and of course, at the end, graph. Okay, so zeros, which will be easy enough for this, right? Middle behavior, I'll show you what I mean by that in just a second. And then end behavior, not that bad either, we just learned that, right? So, first, the zeros. Well, what are our zeros for this polynomial? 0, 2, whoop, -2, thank you, yes, -2, and 4. Right, you just take each one of those factors, set it equal to 0. Okay, so that's easy enough, right? We've been doing that, no problem. The middle behavior, so here's what I want us to do. It's helpful if you take your zeros and put them in numeric order here. So I'm going to do -2, 0, and then 4 like that. Okay, so take those zeros, put them in numeric order, and now what I want us to do is to just pick any number in the interval between our zeros. So what might be a good idea to pick here between -2 and 0? Sure, -1, right? Do you have to pick -1? No, you can pick -1/2 or -3/2, whatever you want, but I like to go for the midpoint. All right, what about between 0 and 4? What would be a good thing to pick? 1 or 2 or 3. I'm going to do 2. Okay, but you can pick 1 if you want to, that's fine. The idea is I want to know what happens, I want to get some idea of what happens between these zeros of -2 and 0, right? If you were to graph these, right, we'd have a point on the x-axis at -2, we have a point on the x-axis at 0. Well, what happens between? Do we go up between the two of those things? Do we go down between the two of those things, right? That's where I want us to kind of, be able to evaluate. Okay? So, of course, we have an x-coordinate. We've got to find the matching y-coordinate, which means we're going to plug these in. So this is g that I described this thing as. G of -1. So we'll plug -1 here into our function. So we get -1 times, let's see here, -1 plus 2 is 1. -1 minus 4 is -5. Negative 1 times positive 1 times negative 5 is positive 5. And so we get negative 1, 5. So there's a point on our graph. And then g of 2, well, we'll do 2 times 4 times negative 2. And again, that's just me substituting the 2 back into the function here. And we'll simplify that to be negative 16. So 2, negative 16. Okay. So between our zeros of negative 2 and 0, does our graph go up between those two zeros? Or is our, let me see. Let me ask it this way. What type of relative extrema does it look like we might have between negative 2 and 0? Does it look like we have a relative maximum between negative 2 and 0 or a relative minimum between negative 2 and 0? Y maximum. Yeah, well, y is positive. We have to go up from the x-axis to that y value of 5 and then back down to the 0. So it looks like we might have a relative maximum in this interval. Okay, I'll show you in a little bit that this is not actually the relative maximum. It's not the location, but that indicates that we will have a relative maximum there in that interval. What about between 0 and 4? What kind of relative extrema do we expect? A minimum, right? Because we see we have a negative y value there. So we would expect a valley, okay, somewhere in there. And again, the bottommost part of the valley is probably not going to happen at this point. And that's because the best we can only find that really with calculus. Okay, sometimes we'll get lucky and we'll actually have it, but for the most part, no. All right, last thing, and behavior, and then we'll graph. Okay, so what is our degree here? What's the degree? To the third, right? Cubed. And what is the lead coefficient? Negative lead coefficient? And it's not a negative. It's not negative. Positive 1 times a positive 1 times a positive 1. They're all positive. So it's going to be like a 1x cubed plus some other stuff we don't care about. Okay. So as x approaches positive infinity, f of x approaches positive infinity. And as x approaches negative infinity, f of x will approach negative infinity. Whew. Okay, and now we're going to put all these pieces together and create a sketch of this polynomial for ourselves. I'm going to do it right over here. Okay. So I'm going to kind of like do a little strategery here. All right, we're going to figure out what our axes should be. So I can see for my x-axis, I've got to have 0, negative 2, and 4, and negative 1 and 2. So I can probably count by ones on my x-axis. For my y-axis, I have to graph both positive 5, and negative 16. So I'm probably not going to count by ones. I'll probably count by 2s on my y-axis. Okay, so let's do that here. All right, so let's see. So 1, 2, 3, 1, 2, 3, 4, 5, 6. I don't know why I went that far, but I did. Okay, and then 2, 4, 6. 2, 4, 6, 8, 10, 12, 14, 16. Okay. You don't need to label every single tick mark if you don't want to, but at least label enough so that I can see what you're counting by, right? So here I put a little 2 just to show that I'm counting by 2s here. And then I didn't label that because I'm counting by 1s. If you don't put a label, I'm assuming you're counting by 1s. Okay? So question, yes. Yes, go for it. All right, so let's plot these points now. I'm going to use a different color so it shows up better. Oh, there you are. All right. So negative 2 is a 0. 0 is a 0. 1, 2, 3, 4 is a 0. Okay. We'll plot negative 1, 5. Negative 1, 2, 4, halfway, 5. Okay. And then 2, negative 16. 1, 2, negative 16, all the way down here. So I can connect these dots, right, from left to right, make them. So that's all of our zeros and all of our middle behavior kind of points. But now we have to add in our end behavior. All right, it looks like as I go to the right here, I should go, just keep going up through to positive infinity. Right, it looks like I should do that. Is that what my end behavior says I should do? As x approaches infinity, f of x approaches infinity. Yes, I should keep going up. Okay. As x approaches negative infinity, as I go further to the left, beyond this point, I should go towards negative infinity, so I do want to go down. Okay. Your graph, yeah, okay, sorry.
Since, like, if it's still, like, an odd multiplicity, don't you go, like, through and then if it's even, it bounces? Do we actually have
Yes.
to, like, find and plot points if we're sketching?
No, if you feel comfortable with using that, then yes.
Okay.
You don't need to do that. Okay. If you are familiar with the multiplicity of zeros and things, you can use that. Okay. But that being said, right? So that being said, right? You do want to be careful here, right? Just because it looks like our graph should just keep going up to the zero or keep going down to the zero, right? You want to keep in mind that doesn't always happen, and it is due to multiplicity. That is like how many times the root occurs, kind of thing. Yes, Claire.
Then what would you do if it didn't happen?
So, well, we'll see that in just a little bit. I'm gonna let you guys see that, okay? So, real quick though, let me just point out, right? Didn't we say that there was going to be a relative maximum between that -2 and 0, right? And there it is. There's that relative maximum, right? It's a hill, right? Here's a relative minimum as well. There's that valley, right? Is this relative maximum also an absolute maximum? Does our graph have an absolute maximum? No, because the end behavior keeps going up towards infinity. Does our graph have an absolute minimum? No. Okay, so there are no absolute extrema here on this graph, for the entire graph, but there are relative extrema, right? Relatively speaking, right, that is a maximum for this little neighborhood of points. Relatively speaking, for this little neighborhood of points, that is a relative minimum. That is the lowest point. Okay, but it's not the lowest point, the absolute lowest point of the graph. All right, so here's one for you guys to try. I want you to do something similar to what I just did there. So f of x equals -2x squared times x minus 2 times x minus 6. Okay? So zeros, middle behavior, end behavior, sketch.
The absolute scrap paper.
Yeah, I think a piece here. Yes, that's it. The homework for tonight or the last tonight's homework? I got you. You're welcome. I believe that's correct. I think I checked it over on the answer key and stuff too. All right, so there. I've given you guys your little blanks you can fill in. Now just. Make sure that you graph the correct end behavior in your graph. Yes?
How do you copy the equation you put above?
Say again, sorry?
Do you copy the equation that you just did, like that you just typed in?
Second enter, or if you can also arrow up and hit enter on the and highlight the thing that you want to copy and hit enter, and it should go back down too. Did that do what you wanted it to do? Did that do what you wanted to do? Yes, that is right. So you want to change your scale so that way you have to, make sure is that your ham and cheese sandwich there?
Oh, yeah.
That was good. Really high. So I would suggest you change your scale. I suggest you change if you want to try and graph it accurately. I suggest you change it. I mean, yeah, I'd like you to graph it. Yeah, that's I see what you're saying. Yeah, like one minute or so, 1 minute or so.
Mr. Wade, did you say
Strategery.
strategic?
Yeah. Yes. It's from do you know the show Saturday Night Live? Okay. Yes, SNL for short. It's from a sketch back when back when it was President Clinton, and no wait. It was when Al Gore was running against President Bush. It was from when Al Gore was running against President Bush, I think at the time. Or anyway, and they were asked to summarize their campaigns in a single word. And President candidate Gore said lockbox, and there was like a joke about that or whatever kind of thing. And then George Bush was strategery. So. because people didn't think that George Bush was very smart, and so they would make fun of how like dumb he was. So, it was Will Ferrell that would play George Bush at the time. Yeah, I can see it. I can kind of see it. All right, folks, here's what it should look like. Something like this. Okay, something like this. Okay. Now, I want to point out, right, that here's what it looks like on the graphing calculator when you use kind of like similar scale. So this is from like, I think, -10 to 180. I'm counting by tens, right? If you guys aren't familiar with manipulating your window here, I mean, you can. So for example, my x-min is -2, my x-max is 10. Okay, my y-min, oh sorry, I made -15. My y-max is 180. My y-scale, I count by tens, okay? You can change how much you count by so it like makes it look not as, messy or whatever kind of thing. So there's the graph, right? Close to what I've got here. I did a similar scale there too. All right, but you'll notice here, right, the way I did this graph, 4, 128, that was the highest point there. That's my relative maximum. But if I actually do second trace and use the maximum command here, my little cursor there, it's to the left of the maximum, so I hit enter, and ask for the right bound, so I'll go to the right of my maximum and hit enter, and then I'll move in for the guess. The idea is you want to put it close to where the actual maximum is. If I hit enter, the actual maximum is located at 4.732, oh, you can't see, 4.732, blah, 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 and then comma 155.13844. So in other words, we are not finding the actual maximum point or minimum points when we're doing this, okay? And because we can't do it without calculus, okay? We really can't do it without calculus. So we will, for some situations, like we can do it for quadratics, right? We can find its maximum and minimum. That's because we are familiar with how to find the vertex of a quadratic and stuff like that. But for this is the best we can do, okay? So that being said, how many relative maximums do we have in this graph? 2. We have a hill right here, so there's a relative maximum. We have a hill right here. That's a relative maximum as well. How many relative minimums do we have? 1 valley, so it's just 1 there, okay? Do we have an absolute minimum in this graph? There are no absolute minimums, because our end behavior goes down to -infinity. So even this low point here, it's going to go lower. Do we have an absolute maximum?
Yes.
Yes, it's going to be in this interval somewhere, right, between these two zeros, because that is the highest point, right? At some point, we're going to reach that highest point and go back down to the 0 there, so we do have an absolute maximum there. So no absolute minimum, but yes, an absolute maximum, highest point. Okay? Questions on any of that? All right. So then your homework will be on Google Classroom. All right, so I will make sure I get that posted here for you. Don't forget also there is that TenMarks assignment, so we're going to have you do that. Tomorrow I think we'll start reviewing for the test. I might also give you an additional 10 marks to work on tomorrow too. So we'll see. Okay. Tomorrow's also a 2-hour early dismissal, so we only get 60 minutes together. I know you're going to be really sad about that, but